Welcome back to Mastering Analog. Today we are discussing problem number 2.2 of chapter 2 of Design of Analog CMOS Integrated Circuits by Behzad Razavi. So in this problem we are given W by L is 50 over 0.5, mod ID is 0.5 milliamps, and we are asked to calculate the transconductance and output impedance of both NMOS and PMOS devices, and also find the intrinsic gain, which is defined as the product of transconductance and output impedance, GM-R0. We are given the properties of NMOS and PMOS model, and which we will be using in our calculations. So again, it's given that W over L is 50 over 0.5, mod ID is 0.5 milliamps. We need to find GM R0 and GM R0 for both NMOS and PMOS. Now, there are three standard equations for calculating GM, and here I have listed for two cases, when lambda equals to 0 and when lambda is greater than 0. This is basically neglecting the channel length modulation effect, and this is considering the channel length modulation effect. So the first equation goes this way: GM equals to mu and COX W over L VGS minus VTH, and if you want to include the channel length modulation, you need to multiply it with 1 plus lambda VDS. The second equation is GM equals to under root 2 mu and COX W over L ID, and if you want to include channel length modulation, you need to divide it by 1 plus lambda VDS, and the square root covers both the numerator and the denominator. Third equation is GM equals to 2 ID over VGS minus VTH, and it's the same for both cases, lambda equals to 0 and lambda greater than 0. It's important to memorize these equations because it comes very handy during design. You can understand if L increases, I can decrease VGS to get a certain GM or something like that. Or if I'm playing with equation number 2 here, if L increases, then I need to decrease ID to maintain a constant GM. So you can understand the effects or trade-offs when you're trying to meet the constraints. All right. So since we are given W over L and ID, I'll go ahead and use the second equation because I can use W over L and ID here. Now for NMOS, and I'm considering the channel length modulation here, so I'll actually be using this equation. GM equals to under root 2 mu and COX W over L ID over 1 plus lambda VDS. Okay. In my previous video, I have discussed how to calculate COX for a given TOX. Please refer to a video that discusses problem 2.1 of chapter 2. So that's one thing. And the second thing is the L used here is again L effective, which is basically L drawn minus 2 times LD. I have discussed this as well in problem number 2.1 chapter 2. Please refer to that video. Now going ahead and substituting the values, we have 2 times mu n for the NMOS is given as 350, and that's 350 centimeters square per volt second, and COX is 35 over TOX. TOX for NMOS is given as 9 nanometers, so it's 35 over 9 femtofarad per micrometer square. And again, W over L effective, 50 over 0.5 is the L drawn minus 2 times LD. LD is given as 0.08 micrometers times 0.5 milliamps, that's the current ID, divided by 1 plus lambda for NMOS is 0.1, given as it's given in the properties, times VDS is supposed to be assumed 3 volts if you look at the problem statement. All right. Now again, bringing all the units to one standard unit. So we are going to write 2 times 350. I'll convert centimeter square to meter square. So I'll need to multiply by 10 to the power minus 4 because 1 centimeter is 10 to the power minus 2 meters. And since we have a square, it will be 10 to the power minus 4 meters square per volt second. Times 35 or 9, I'll convert femtofarad per micrometer square to farad per meter square. So femtofarad is 10 to the power minus 15 and 1 micrometer is 10 to the power minus 6, and since we have a square, it's 10 to the power minus 12. Times 50 over 0.5 minus 0.16, that will be 0.34, then 0.5 into 10 to the power minus 3 amperes, divided by 1 plus 0.3, which gives us a GM of about 3.92 millisiemens. Alright. Just so that you know, GM is basically the slope of ID VGS curve. Alright. And R0, which is the output impedance, basically is the inverse of the slope of ID VDS curve. Alright. And it is given as approximately 1 over lambda ID. So going ahead and substituting the values, lambda is 0.1 and ID is 0.5 milliamps. So that gives us an output impedance of 20 kilo ohms. Now the intrinsic gain, which is given as the product of GM and R0, is just this. We have GM equals to 3.92 millisiemens and R0 of 20 kilo ohms. So GM R0 is basically 78.4. The units are volt per volt. It's basically unitless. It's nothing but the gain. Alright. And the intrinsic gain implies that this is the maximum gain you can get out of that particular transistor. Alright. Now similarly, going ahead and calculating for PMOS, we have GM equals to under root 2 mu P CMOS W over L times ID whole divided by 1 plus lambda mod VDS. Alright. So substituting the values, we have under root 2 mu P for PMOS is given as 100 centimeter square per volt second. CMOS again is 35 over TOX. TOX again for PMOS is 9 nanometers. So 35 over 9 femtofarad per micrometer square times W over L effective. LD for PMOS is given as 0.09 micrometers. So you have 0.5 minus 2 times LD times 0.5 milliamps, which is ID, whole divided by 1 plus lambda in case of PMOS is given as 0.2 and VDS is 3 volts. Again, converting everything to a standard units, we have 2 times 100 centimeter square is converted to meter square. So you need to multiply with 10 to the power minus 4. 35 over 9 femtofarad per micrometer square is converted to farad per meter square. So you need to multiply by 10 to the power 15 over 10 to the power minus 12, as we did in case of NMOS. Then we have 50 over 0.32 and 0.5 times 10 to the power minus 3 whole divided by 1 plus lambda VDS turns out to be 1 plus 0.6. That gives us an effective GM of 1.94 millisiemens. Again, R0 is approximately given as 1 over lambda ID. So 1 over lambda in case of PMOS is 0.2 times 0.5 milliamps. That gives us R0 of 10 kilo ohms. And the intrinsic gain is given as the product of GM and R0. So 1.94 millisiemens times 10 kilo ohm gives us an intrinsic gain of 19.4 volt per volt. So this is the simple solution for problem number 2.2. The key points here are to remember the equations for GM and how that varies with lambda when lambda equals to 0 and when lambda is greater than 0. And also knowing what GM is, basically what R0 is and what the intrinsic gain is. So this is what we learn through this problem. Thank you for watching, and in the next video we'll be discussing the solution to problem number 2.3. Thank you.